Hello, I am Rajesh Gupta, and on behalf of Holtec, I am here available you for the presentation of mastering power distribution with ETAP and ILMS, a smart sports approach to multi-source, multi-load system. Okay, let me introduce myself first. I am an electrical engineer having around 40 years of experience, out of which last 20 years we are with Holtec and executed many projects. Okay, so to start with, as the topic suggests, there is two things which we have to discuss. One is ETAP software, and the second is the integrated load management system. To start with, let us start with ETAP software. Uh, ETAP software is a specialized software tool for electrical power system modeling, design, and analysis. Okay, this is a offline simulator. What does it mean by offline simulator? We can model the power distribution system in ETAP software. We can simulate any kind of situation in your power distribution, like any fault, any overloading, any sort of operation. We can simulate, and we can check results of those changes or what inputs we have simulated in the model. So we can get the outputs. So these with the help of those outputs, we can analyze the things, and we can conclude what exactly will be the requirement for our power distribution system to take care. So this can be used to optimize not only project engineering, but also can be used for plant operation, and also will be used to integrate new sources and of power or loads, as this is very common in cement industries. Now we are adding multiple sources and multiple lines. Okay, in Holtec, we have latest version of ETAP software, which is suitable to handle 500 buses. Now, what are the studies which can be offered by Holtec on ETAP? We offer almost every sort of study which is required for power distribution system. Maybe it can be a short circuit, can be a load flow, or whether it is relay coordination, whether it is transient stability or motor acceleration, arc flash, harmonics. We have all modules available for these studies in our software in Holtec. And not only that, we also design and implement high-speed integrated load management system depending on the need of the power distribution system of any kind. Next, let us start to discuss about the various studies which can be performed on ETAP software. So to start with, we can do it with short circuit studies. Short circuit studies, sorry. Yeah, short circuit studies, it is recommended during project stage. If it is not available, the study data, if it is not available or not done, it is advised to do it for running plants also. If you want to identify the safe operational modes for operation of a plant, you know, in our power distribution system, we have tie feeders, bus couplers, and so many flexibilities we are keeping. So we have different operational scenario which we can create in our power distribution system. So here in ETAP, without doing any online analysis, we can do it offline. We can simulate, we can create all possible operational scenario and check the performance of the short circuit currents. Okay, and it is also recommended, if you are adding new source or major loads, then you have to conduct these short circuit studies. What is this? These studies. These studies is what is short circuit studies? It is an analysis of an electrical system to identify the magnitude of the fault current during any electrical fault if we create in the system. And when we compare these calculated value against the equipment rating, we can decide whether our equipments are properly rated, or we can design the equipment according to the fault magnitude which we can simulate, which we can find from the results of the ETAP short circuit studies. Okay, so this will help not only to decide the equipment rating during project stage, we can also validate the equipment rating when we do the modifications in the system. Okay. In Holtec, we have a latest version of ETAP software, which is suitable to handle 500 buses. Now, what are the studies which can be offered by Holtec on ETAP? We offer almost every sort of study which is required for power distribution system. Maybe it can be a short circuit, can be a load flow, or whether it is relay coordination, whether it is transient stability or motor acceleration, arc flash, harmonics. We have all modules available for these studies in our. What are the results which we can obtain from this short circuit studies? The first thing is that all buses and the associated equipments rating we can validate or we can decide. Okay, so that your system will be safe. So the next one is the safe operational scenario amongst all possible options. So that I have already tell you that there are multiple operational scenario available in any power distribution system. So we can check which are the safest one to operate. Then we can also validate the addition of new power sources and major loads. And the last but not the least, it is very useful requirement to conduct a power coordination study. This is an example. This is a typical example which we have performed in one of our studies, where we have 3 power transformers connected power of grid to the plants, and 1 power plant, 2 waste heat recovery systems. So total 5 sources are there, and 2 cement lines are connected. So here detail of cement line is not given because of the space limitation. So we have studied this system. Now we have done the analysis in many conditions. In the condition number 1, where our CPP system is not in parallel with grid. It is running in island operation. So here this bus coupler is open. So this complete load is totally disconnected from the grid. And what we see, there is a fault level available approximately 26 kiloampere on both sides of the buses, both sides of the bus couplers. And since the rating is 40 K, so system is safe in this condition. What are the results which we can obtain from this short circuit studies? The first thing is that all buses and the associated equipments rating we can validate or we can decide. Okay, so that your system will be safe. So the next one is the safe operational scenario amongst all possible options. So that I have already, but when we make our bus coupler on, which means when we are making this CPP and grid in parallel condition, what is happening? The fault levels on both sides of the buses has increased substantially. It becomes 52 kiloampere fault level on the CPP bus. So against the rating of 40 kiloampere, so which means that it is not advisable to operate without having any preventive measures or preventive action to take care of these high short circuit currents in the system. So this is a typical example which I am giving. This can be a very small portion of a complete power distribution network. Where in this study we can even we can check the fault levels on the LV buses. Up to LV buses we can do and check any fault levels. Okay, so this depends. This is the cut portion of a complete study SLD. After the SLD, this is a tabular form of study results, where we have done it for 4 different conditions, and we found against the rating what are the fault levels in various operating conditions. So in that way, we can give you the things which condition is safe, which condition is not safe. So this will help you while you operate the plant. The next is the load flow study. What is load flow study? It is basically a study which is being done during steady state or normal operating conditions with various operational scenarios. Same as we have done for short circuit study, here also it will be done for this normal operation. for different operational scenario. In load flow studies, we basically achieve the aim is to achieve the economical operation of the power system, where the efficiencies and the losses can be optimized, voltage levels will be optimized. Okay, so this is basically the function of this is basically the objective of the load flow studies. And now coming to the load flow results. The load flow results, we can ensure the continuous rating of the various equipments and the branches, the bus bars or the cables. Okay, then we can also observe the power flow pattern, both reactive power and active power. Power flow patterns in complete power distribution network. Then we can check and optimize the voltage profiles at different buses of the system. So here, when we will get the information of the voltage profile of the on different buses. So based on the result, we can do the corrective. We can suggest the corrective actions to optimize the voltage profile. Why this voltage profile optimization is required? There is actually speaking, with the higher voltages, the losses, the fixed losses basically, because we have all inductive loads majorly, whether it is transformer, whether it is generator, whether it is motor, all are inductive loads. So in inductive loads, what is happening? This fixed losses or iron losses are square of voltage. So the moment we increase the voltage to its rated value, then your fixed losses in these equipment will increase. So if we optimize the voltage, we are able to reduce the fixed losses in the system, especially the equipment, transformers, generators, and motors. So this is what is a requirement. That is why we need to optimize the voltage. The second one is to optimize the power factor. Power factor of the generator, grid, and various buses. Okay, grid we can understand because it is related to the tariff. It is related to the cost we are paying to the grid. For generators, the same reason. If we if in generator, if we operate generators with lower power factor, what is happening? The copper losses. The copper losses, which is dependent on the I square of the current, will be increased, because with lower power factor, for same power output of the generator in terms of kilowatt, the current will be more. So when the current will be more, the load losses or copper losses which is happening in the generator itself will be high. So this is what is my personal observation, that normally people are not concentrating on the power factor improvement of the generator. Rather, generator has been used as a tool to maintain the unity power factor on grid, irrespective of the power factor which we are maintaining on the generator, except not less than 0.8, which is the rated one. Okay, but if you operate the generator with 0.8 power factor, and if you operate the generator with 0.95 power factor, there will be a substantial decrease in the load losses in the generator itself. And the generator load losses is approximately 35 to 40% of the total losses which is happening in the generator. So you can understand, if it is 90%, 96% efficiency of the generator, the amount of losses which you can save, you can very well calculate. Then we have to maintain not only the power sources where we have to maintain the power factor, we have to optimize the power factor on all buses. The buses means the branches from where the incoming power is coming and it is distributing to different load or different buses. So these buses power factor, all buses, whether it is MV, whether it is LV, we have to maintain the power factor. Why? Because when we maintain the power factor of that particular bus to near unity, then the incoming power which is being received by this bus from various sources will be the current will be reduced. So the branch losses, the cable losses, which is a connection between the source and the bus, will be reduced. So your losses will be improved. So these are the very two critical parameters which we can set from load flow studies. Not only that, we can also do so many other observations, but these are two very critical observations. So in that way, we can minimize distribution losses and also optimize the equipment efficiencies. Okay. Now, next is an example. Here, this is a portion of a study result in one of the project where we have. This is the existing situation where it is being the power is being received from the grid, and we have a main receiving station where we have two different buses where the bus coupler is in open condition. So the load is being there on both the power transformers. So here the overall power factor we are able to maintain. But what is happening? This power factor in this area is okay, but here it is actually on leading condition. So what is happening? The result of this leading power factor is the increase in the voltage, distribution voltage or of that particular bus. So you know when the voltage will increase, your fixed losses will increase, and this is also not advisable to operate the plant with leading power factor at any of the buses. Okay, so after optimizing the voltages through the corrective actions, we have been able to maintain 99% power factor, which is absolutely perfect as against 0.88% leading. And here you see the power consumption is also reflecting. There is a reduction in the power consumption without doing anything. We have just optimized all the buses voltage and the power factor, and what ultimately we get is the saving in the overall power received from the grid. So this is a classical example where you can say that it is not by optimizing the power factor, by optimizing the voltages, you will have saving from in the power which we receive from any of the source, not only grid. This is another example where we have a generator, and here what is happening in generator, we are maintaining 6.7 kV voltage, which is slightly on higher side. Here also on LV we have 438 volt as against the 415 volt, what is our requirement. Okay, and last but not the least, the power factor on the LV bus is very poor. So when we have do the corrective actions, we are able to maintain the power factor of this LV bus nearly unity by adding the capacitors, APFC, and also we have optimized the voltage. So overall effect you see here it is 152 K. This is actually KVA. All these parameters are shown in KVA and PF. So this is 152 or 153 kVA, which was the load, which has been drawn by the load, has been reduced to 111 kVA. So this much amount of saving will be possible if we optimize power factor and the voltage. But not only this, here you see this 6.7 kV, we have optimized to 6.5 kV, and this is also giving some benefits. So this is the things. This is our ETAP report summary, where we can find the losses, especially the branch losses and the losses in the transformers. So when we go through these parameters, we can see where we have a potential to improve, and accordingly we can take corrective actions in the system, and subsequently we can achieve lesser overall distribution losses. You see this in this particular case where we have two cement lines, four this power transformers, and about 1 WHR as a source. The total MV distribution losses, not only in motors and generators, only in transformers and the branch cables, is coming in the range of 466 kilowatt. So this is huge, which you can save. In this particular project, we have given the recommendations, okay, to reduce the power factor, reduce the voltage, and some other recommendations. All is not possible to show you here in the slide. We here you see in our saving potential sheet, we have given the recommendation, we have given the benefits, we have given the saving in terms of kilowatt. What is the saving potential in terms of rupees per rupees lakhs in a year? What is the investment which we have to do, and the payback? Here, as I have shown you, by changing the mode of operation, the mode of operation in which the plant was running, we have suggested just change the mode of operation, and there will be a saving of around 61 kilowatt without investing anything, without doing any action in the power distribution system, any corrective action. Just what we have done, we have changed the mode of the operation. So nothing has been done, and it has been implemented immediately. Okay. So I'm just giving example. It is not. I'm not saying this will be this can be possible in all of these studies, but here in this particular case, we have achieved like this. But there are so many things which is possible in terms of saving can be found through these studies. Now coming to the protection, because we have covered short circuit, we have covered load flow. Now we can cover protections and relay coordination. So what is the objective of the protection? The objective is very clear. We have to identify the fault in the system. We have to automatically initiate the action to isolate the faulty equipment or the section. And the motive was that we have to ensure minimum disruption to the healthy part of the system. This is our main objective when we do the protection system design for a particular power distribution system. This protection system will prevent or minimize the damage in the system, right? Why? Because we are reducing the arc flash energy with quick identification and rapid disconnection of the faulty equipment or section. So in that way, we are either preventing the damage or minimizing the damage in the equipment. It is not 100% sure if your relay will work perfectly, then there will not be any damage in the equipment. No, it is not like that. When there is a fault, definitely some damage has already occurred in the system, but we can minimize that damage. In cases, there are some cases like overloads or some under voltage condition or over voltage conditions. If these kinds of protections is operating, in that we can even prevent the damage of the equipment. So it is not that in 100% cases it is ensured that if equipment protection is operating means we are saving the damage of the equipment. Now let us discuss the stages of the fault clearances. When any fault has occurred, what stages are there in the fault clearing? So the first is the occurrence of the fault. Then we have measuring instruments through which we do continuous online measurement of the operating parameters. And whenever the fault will occur, this will give the reflections in the instrument transformers, and those will be analyzed by protective relays and initiative or selective tripping. Okay, here the word selective is very important. Hello. 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 Can you mute your? Yeah. Thank you. Analyze of the protective relay for initiating a selective tripping. Selective tripping is a very important aspect in any protection system. Okay, this we will discuss later in the slides. And when this relay will check and initiate a selective tripping, a switch gear which will clear the fault, which will trip, which will off and clear the faulty sections or faulty equipment. So in that way, these are the various stages. Now coming to the relay characteristics. What are the characteristics which we have to have in the relay to operate, which will make it very reliable and sensible? Okay. So the first but very important is the speed. It should have a speed to make very fast decisions. If it makes very fast decisions, the damage which is due to the current will be minimized. The moment, as soon as the fault will be analyzed and the tripping will be initiated, then the damage due to the fault current will be minimized. Not only minimized, we can also ensure the system stability. This system stability we will discuss in detail further. Then the next characteristics is security. Security means the malfunctioning. Malfunctioning should not be there in the relay. That means it should not open the switchgear, or it cannot initiate the tripping during normal conditions. Then third one is dependability or reliability. It means in any abnormal condition, it should be ensured that relay should cause system to disconnect. Then sensitivity means ability to detect all abnormal or fault condition. Sensitivity means when it depends on the amount of power which is flowing in a system. Suppose if in a system very say negligible amount of power is flowing, so whatever instruments or whatever relay we have produced, there can be a problem of the sensitivity. They cannot sense the fault current with this minimal loading condition of the system. They cannot sense the fault current properly, and so we have to design a relay in such a way that even with whether it is very less loading of condition, whether it is overloading condition, in all possible conditions, my relay should able to sense the faulty condition and initiate trippings. Then last but very important is the selectivity. Selectivity is the ability to discriminate between fault, whether it is internal or external, to its intended zone of the protection. This means then which circuit breaker or which switch gear it will give the tripping, or which relay has to give tripping to what circuit breaker. Okay, so this we can discuss further in next slide. Okay. There is another phenomena which we normally discuss. It is primary protections or backup protection. What does it mean? A device closest to fault, device means relay, closest to fault offers primary protection. Any device which is very near to the fault will give you a primary protection. And the device or relay next in line, after this first device which gives you primary protection, will offer you backup protection for the same fault. Okay, what does it mean? If primary protection device fails to clear any fault, a backup device will clear the fault with a determined delay of the time, which is a time grading between these two devices. To elaborate it further, let us check this example where we have three fault situation, F1, F2 and F3, and we have three devices, one fuse, R1 and R2, two relays, and FU1, one fuse. So these three devices and three fault locations. So for this FU1, this device FU1 is a primary protection device for fault F1. So this is the nearest one. So this will offer the primary protection for any fault F1 which is happening here. Okay. And for R2 is the primary protection for any fault in F2. But it is also giving you the backup protection for the fault F1. And same way, R2 is the primary protection for fault F3, the first backup protection for F2, and second backup protection for F1. So in that way, the fault clearing process we decide and we define. Okay, and for those things we have to have a proper coordination, so that there should not be any incidents where if fault F1 has happened and either relay 1 or relay 2 will clear fault before the actuation of clearing of fault with FU1, which means multiple bigger zone of healthy equipment also will be affected. Okay, so this is what is the meaning of a relay coordination. So this is basically the purpose of the relay coordination. So why relay coordination? I have already give you some brief of the relay coordination in previous slide. Here it is basically in relay coordination we define the characteristics of the relay, rating of the equipments, measuring equipments, and the protective relays we have to decide, and the various setting, what settings we have to impose on those relay so that we can have effective protection. Then we can achieve good and reliable selectivity. Selectivity means I have already explained you. If a fault, as in the previous example, suppose if it is fault is happening at F1, for F1 fault, the device which has to operate is a FU1, not R1 or R2. So this is what is a meaning of a selectivity. So we have to do the grading of the timing in such a way that first the fault will be cleared by FU1. If it is not there done, then it will be taken over by relay 1, and ultimately if it also fails, then it will go to the relay 2. It is not only the thing. In many of the plants, when we have a proper relay coordination, then we will get the diagnosis of the fault, diagnosis of the faulty zone. We can clearly define what is a area of the fault where the fault has happened. So my total efforts will be confined to that faulty area only. Suppose if no relay coordination is there, then there will be a bigger area of area which we have to investigate. And we really know, maybe it's not only one equipment. Suppose if one motor protection is operating, our total efforts will be to check that particular motor for the fault. But if our LV switchboard incomer is tripping, then we don't know. There are 50, 60, 70 motors which are connected to that particular device. So how can we identify the fault? So this will give us this will not only give us the fault, fast clearing of the fault, protecting the equipment. This will also give us or pinpoint us the correct position of the fault, so that we can take corrective action very fast and restore the equipment as early as possible. So when we have to do this relay coordination, so when it is to be done, so the ideally when you are in project stage, then you have to have a proper relay coordination. Okay, then if you are adding or modifying the system, you are adding any load, you are adding any source, or you are changing the rating of any major equipment, then there is a need to do the relay coordination again. Third, there is one more condition where you can redo the relay coordination. If you are feeling these abnormal trippings, which means a tripping of the incomer without identifying the fault in the bus. It is happening actually in one of the motor which is connected to the bus, and my incomer is tripping, or any motor circuit breaker is relay is operating, and we are not able to find any fault or any such kind of issues which is not happening, which is not actually operating as per our desired protection philosophy. So then it is a time to check relay coordination again. And the relay coordination, there are methods. We can do the relay settings and the coordination through Excel calculations also. Okay, but these Excel calculations have some limitation. No, we can define one particular type of quantum of current, and for that we can do the settings, and we can do the gradings also for different relays which sense those fault conditions. Okay, but it is in power distribution system, you cannot define the amount of fault which is actually passing every time. Why? Because fault may occur at any position. The fault will be of dead short circuit nature or dead ground nature, or it can be a partial short circuit or partial ground. So the amount of fault current which is flowing in different fault conditions will vary very widely. So if we take any this calculation which is through Excel will not give the sufficient proper coordination of the system. Then what next? What next we have solution? The solution is the settings through software, where we can have a selectivity curves. This coordination curves or selectivity curves we can achieve from the software. So this curve is basically the fault current in horizontal axis and the time of operation in vertical axis. So in this particular network, we have two relays, relay number 1, relay number 2. So for this fault serial number 8, which is happening here, the ideally this, as per the principle, relay number 1 is our primary protection and relay number 2 has to be a backup protection. So here the entire range of the fault current, we can find out the coordination curve. Okay, so we know this is the amount of current here in the fault. What should be the time of operation? So the moment the current will be less, the fault time will be high. Okay, so in that way we can get this graph of this relay 1, the characteristics curve. Okay, and the same way we can also achieve the relay characteristics curve for relay 2, and we can with this software, with the help of the software, we can do the proper grading. You know, in our system, when we do the relay coordination, there will be minimum grading time because of some limitations of the operational characteristics of the circuit breakers or operational characteristics of the relay and other associated equipment. Normally with new relaying system with numerical or microprocessor based relays, still we recommend at least 150 milliseconds of time grading should be achieved. So this time grading minimum with 150 milliseconds or more we have to achieve here to ensure that relay number 2 should not operate for any fault which is happening here. So in that way, the entire range of the fault current, we are in a position to validate that my relay 2 will never operate before relay 1. So this we can achieve. So there we can have 100% surety, we can have 100% reliability with respect to the coordination which we can ensure. Okay. Not only this, in this curve we can also get these lines. This 4 and 5 are the peak values or peak withstand values of the equipment. Okay, so this equipment should not have current more than this curve. Suppose this number 4 is what? Number 4 is the thermal withstand capacity of line 1, this line 1. So if in any case, if any current which is going beyond that number, then there will be a problem in this line 1. So both the relays are protecting this line 1 without having the peak limit of the withstand capacity of that particular line. So we can also identify the withstand capacity in the curve. It is also giving me the values where my normal starting current or running current should not be overlapped with this settings. So my setting should be slightly on higher side to the maximum value of the starting current or inrush current or running load current. So in that way, we can properly ensure the operational reliability and sensitivity and selectivity. So with this curve, which we can obtain through software, our relay coordination will be almost foolproof. This is the outcome of a ETAP software relay coordination. Okay, in one of our projects. We can also get the settings, device settings also through this software. Then we can also give our recommendations or suggestions for the protections. Maybe some protections we may add, maybe some relay we can change the model, or we can suggest some other ways of doing the things. So in that way, when we do the audit, we can suggest you. many of these kinds of suggestions with respect to the protections. Now comes to next is the power system stability. Power system stability is a property of power system containing minimum 2 or more machines. This is applicable to a system which contains 2 or more machines. And what is this? It is the ability to return to normal or stable operation when any system is subjected to any form of disturbance. When there is any disturbance in the system, it should have an ability to return to its normal or stable operation after that disturbances. So this is called the stability. So it can withstand the disturbance and resume the normal stable operation. So this is the definition of the stability. We have normally discriminate the studies in 3 types: steady state stability, dynamic stability, or transient stability. Steady state stability is basically the normal operation when we increase or decrease the load with predefined interval, or do it gradually without losing the synchronism of the in the system. So we have multiple sources if it is operating. So when we change the loading, or when we change the loading on any of the source or any of the load, it should not lose the synchronism of the system. Okay, so this is normally during normal operation. So we tune our system in such a way that it can withstand these variations when we change the loads. Dynamic stability is a stability where we have small disturbances occurs. This you can visualize when you start a motor. Then there will be a starting kick. This starting kick may be in the range of 6 times, 7 times, or 200% or 300%, depending on the type of starter. So this is a kick load which is coming when we start the motor. So this gives us a sudden change in the load of a considerably higher magnitude. So there will be an oscillation in the operating. Suppose I'm just giving you an example situation where we are not connected to the grid. We have only one generator which is operating, which is managing the entire load of the plant. So when we start a motor, so because of this starting kit, what will happen? There will be slightly reduction in the speed. So there will be an oscillation in the speed. So this oscillation will be of very small in nature and will vanish very quickly. So in that way, so these two, the steady state and the dynamic stability, this is basically happen during normal operation of the plant. And now comes to the transient stability. The transient stability is a large disturbance. You can visualize in that way only. So what is happening? These large disturbances will cause very large changes in the speed of the rotor. Okay, or power angle. So if the speed of the rotor will change, your power angle is means stator and the rotor, the angle between the stator and the rotor magnetic field. So this will also change. And okay, so this, your transient stability will give a bigger variations in the rotor speed. So in that way we can understand. So now come to the transient stability studies. Now for dynamic and steady state, there is no need. We have to do simply the tuning of the governor, tuning of the AVR, and we can achieve the dynamic and transient stability stabilities. But for transient stability, we have to do some study on ETAP software to ensure whether our system has a transient stability or not. So why? How? This study, what is this study? A dynamics of power system during large disturbances, which is either a fault on generator terminals or grid side, or loss of generation and of any of the source, or loss of load like this. That means a huge change in the power. Okay, or huge demand of the power, or huge throw of power. So this is the way This is a study for check the dynamics of the power system for these kinds of conditions. Now, what is happening when we apply these kinds of faults? There will be a fast change in the angular swing of the rotor. So generator rotor will have a, because what is happening? The generator, suppose if it is one generator which is operating for our understanding. So what is happening when there is a fault happening in any of the motor, or a fault which is happening in the grid through which this generator is running parallel? So what is happening? This generator will start feeding fault current. So what is happening? There will be a considerable amount of, huge amount of load which is exerted on the rotor, and which what it caused? It caused the rotor to slow down. Rotor to slow down. If it is a throw of loads, then the generator speed will go high. But if it is a fault, then what is happening? The generator speed will be down. So what is happening? Our system, which is governor or any AVR system, our response, their responses will start working. And what it, because it is tuned for your steady state or dynamic conditions. When there is a transient condition which is happening, what is happening? Their responses are not tuned for those transient conditions, cannot be tuned. So what is happening? There will be a oscillation. So your speed will go up, go down, go up, go down, like this. So till, and it depends on what? It depends on the angular swing, the amount of the angular swing, the first swing, which is happening in the system, and the critical fault clearing time, how much time this fault is appeared in the system. So the duration of the fault and the amount of the first angular swing, means the amount of the sensitivity of the fault, or severity of the fault rather, severity of the fault and the duration of the fault. This will give you the things which is creating the oscillations bandwidth. Okay. And during such disturbances, all connected loads, because all sources are connected in parallel, so everybody has a tendency to feed fault. Okay. And when we clear this fault disturbance, these parameters of each generator will try to retain to its original position to the shortest possible time. If the stability is ensured, then every generating sets will come to the normal steady state condition. If the transient stability is failed, then what is happening? Your generator will trip. And how it can be checked in ETAP? So this study performed with various operating parameters and fault conditions. We have to analyze the various operating conditions with various types of faults. Okay, so this we have to identify, and then we have to do the analysis for every condition and every fault condition and every operating condition. Okay, then what we have to do, we have to establish a critical fault clearing time. What it means? We have to apply the fault, we have to check the fault duration, where we are actually any time we are critical fault clearing time, we are setting in the system software, and check whether the stability is achieved or not. The critical fault clearing time is a time beyond that the stability will not be achieved. So critical fault clearing time means a fault condition in a system. Beyond that, if we are not clearing the fault, the system will become unstable, or any of the component, maybe any of the generator, will become unstable and results into tripping of that particular entire system or that particular generator. Okay. So what we get the result? We get the results in terms of curves like power angle, generator electrical and mechanical power, speed, voltage, behavior during that fault condition and after that fault condition. Immediately during the fault condition and after few seconds of the fault, what is happening in the system for individual power source. So the method which through which we can show a certain the stability is that we check the first swing degree. We check the first swing degree, that is power angle degree, and my power angle first swing in the power angle, if it is below 100 degree, and after that we have subsequent decreased this swings, that means my disturbance are getting damped, and my source will retain the stable operation, steady state operation. Okay, so when when we find out for that particular generator or all of the generator, which one is which is the least possible fault clearing time for all the generator to ensure stability, that is my critical fault clearing time. And now we have to ensure that our protection relay should be set well below that fault clearing time, so that our entire system will be stable for any such kind of transient. This is a power angle which we have discussed in the previous slide. Here you see, here the fault has occurred, and in 100 milliseconds or 150 milliseconds, whatever the clearing time we have cleared. So this is what is my first swing. So this first swing is below 100 degree. So this give me first assurance that the stability will be retained, and then it is followed by a decreased bandwidth of the fluctuations. Then that means we are, after some time, the system will become stable. So this is for a fault in the grid system. We have created fault in the grid system, and we have checked the performance of all our other generators. So here in CPP1 we have checked like this. This is a graph for CPP1. Same way there can be some other sources also, maybe WHR, maybe another CPP. So that also we have to check for similar kind of curve to ensure the stability for that particular fault clearing time. This is an example. This is a critical example where we have 3 grid transformers, 2 CPP, 2 WHR. So there are you can say 4 plus 3, 7 sources are there. Okay, and we have multiple lines connected to this distribution network, and here we have created the fault. Okay, a 3-phase short circuit fault on grid. Okay, fault as we have created at 0.5 seconds. We have cleared cleared the fault at 0.65 seconds. This we have done the simulation, right? So that means the total fault clearing time is 150 milliseconds. And then we have examined all these curves. Okay, this is generator megawatt curve. Okay, so if we find, we can check, we are able to retain the stability. So if it is validated for all the sources, we can recommend that our setting should be like that. It should be in such kind of transient, the relay operation time should be less than 150 milliseconds. So in that way, we can give our recommendations, and with that, we can ensure the system will be totally safe for such kind of transients which is happening in the system due to fault conditions or any abnormal load flow, switching of the generators, or any major load switching off, or any major load throw. Okay, so in that way, if we check, this will assure us nothing will be 100%. There will be some chances there. Even after that assurance, there can be a possibility, because 100% cannot be possible in any of the studies. There can be 1%, 2%, 3% chances that there can be some in any of these very abnormal conditions, there can be a possibility that there will be a loss of stability. It may be because of our study errors. It may be because of the operational speed of the fault clearing system. Maybe relay sluggish, maybe breaker sluggishness. This may result, because here we are talking of 100 milliseconds or 150 milliseconds. Now, coming to the power distribution, what is its importance in the cement plants? Cement plants are power intensive, sorry. Approximately 30% of the production cost is power cost. So this we all know, which means the availability, power cost, reliability of the power, and the minimum stoppages will play major role in cement manufacturing cost. If my power cost will be less, definitely my cost of cement manufacturing will be less. Why stoppage plays major role? Because during stoppages there will be unproductive consumption of the power, which is actually we are paying without any production. So that is why we have to have an minimum stoppages on account of any power distribution issues. And why this is to be checked and assured? Because we have to be competitive in terms of power consumption and in terms of the cost of power, uh, so that we can become competitive in the market. Okay, the next is uh, what happens to the cement plant power distribution, which makes it complex. Okay, what is happening? We have, because of this issue of optimizing the cost of power, optimizing the power consumption, we have done various measures. So what measures? For reduce cost of power, we have added many sources like grid, CPP, WHR, solar, wind, and so on. So we are adding varieties of the sources now in our existing cement power distribution. Then to reduce power consumption, we do many modifications in the system. Okay, it can be major modifications also, it can be minor modifications also, but we are specifically concentrating on the major modifications. Then, because the cement growth is very rapid, so so to meet the growth, what plants are doing, they are adding multiple lines in same location. In same location, now we have one plant. Now we are having maybe 3 plants, 4 plants like this. Okay, so with these actions, what is happening? the, the because of this, our power distribution system has become complex. Because what is happening here, you can say in Hindi, if we say sone pe suhaga, what is happening? We are doing so many modifications in the power distribution system, but those modifications are not at once, they are doing at regular intervals. So because of this, our distribution system is becoming now very complex. So what is the issue or challenges with complex power distribution? Now, we know our system is complex. Now, what are the challenges? Now we are actually facing blackouts. Yes, we are, because of the complexity in the system, many of the times we see that complete blackout in the plant. Cascaded trippings are there, because one system is tripping, resulting another system is tripping because of this tripping. So in this type of cascading trippings also happening. Now what is happening? We have multiple lines, maybe 3 lines, maybe 4 lines. In some cases, 4 lines are running, right? So what is happening? We have different sections in the plant lines. So we have multiple loads, which is available for load shedding. So now there is a requirement of prioritization of those load setting. Maybe, for example, today at this moment of time, we have the least priority load will be maybe cement mill for line number 1. Okay, but there is a pressure. Maybe after a day or next day, or maybe after 8 hours, there will be a huge demand for cement, and then cement mill operation will become very critical. So the priority will shift to say raw mill for line number 2. So in that way, we in real sense, the dynamics of priority is changing on real time. So it is not that it is fixed kind of priority you can set. Now your prioritization will change based on the need of the hour. So we should have a system in which we can achieve the priority load shedding. So this is also one of the challenge. Then the another challenge is load sharing. Load sharing, here we can have two types of condition. One condition is when we are running in parallel with the grid. Normally, what is the scenario nowadays? We draw minimum power from the load and try to get our own generation maximum. Okay, but what is happening? You have a fluctuating load. Your load is not fixed. Your load is your plant operation is not fixed. Sometimes some load is running. Say 20 megawatt is running. Sometimes it is 50 megawatt is running. Like this, we there is change. There is a change. There are fluctuations in the loads. There are fluctuations. Sometimes these fluctuations are in the range of 2-3 megawatts also. So what is happening? And suppose we want to keep 1 megawatt on the grid. What is happening? And we have a reverse power tripping also. What is happening? Because of this fluctuation, your load on the grid will become zero, and your reverse power will operate. So what people are doing? Then what we do? We switch. We bypass the reverse power, and this slight variations in the load is actually going reverse to the grid. So this is happening. Okay. So the same way, if we are doing the export, suppose if we are doing the export, so suppose we have to export say 5 megawatts, but because of this fluctuations, sometimes it is not possible to fix 5 megawatt pakka on the grid side. We cannot give the set point for the export, power export, and control our source power drawn. Okay, so this is not actually possible with this complex power distribution. Now another condition, when suppose we are running in island operation, only no grid, only generators are there. So suppose if we have two generators, two CPP, one is efficient, another one is less efficient. So what is our tendency? What is our requirement? We have to take most of the power from the most efficient one. Okay, but that most least efficient one is our when we run in the island mode will become the master. So that will take care of the fluctuations and other loads, and the other one we can fix the load. Okay, so if it is in that way, what is happening? We are not able to fix set the load on both the generators based on our requirements. Maybe 75% on one generator, 25% on another generator. Not like this. We cannot run because of our limitations. Okay, so now this we want to do. Okay, now the power cost. Power cost is very important. We have to take power from our cheapest sources, maximum power, and minimum power from our costly sources. So this we have to do. MD control is everybody knows. Okay, so we cannot exceed the maximum demand from grid to a defined value. Otherwise, we will be penalized. So this also is a challenge for us. In any case, our MD should not exceed. Then loss of production. So when we have a nuisance trippings, when we have unprioritized load sheddings, okay, then what is happening? It is resulting into production loss. Okay. Now, as next is power factor and distribution losses. What does this mean? For various buses, if we, as I told, we have to maintain the power factor, but there will be a variations in the load on the various buses during the operational condition. Entire operational condition, the load is not fixed; it is varying, and when it is varying, your power factor will also vary. Okay, so according to the varying load, we have to switch on or switch off the capacitor banks connected to the bus. So for LV, we do with the help of APFC, automatic power control relay, but in MV, it is not possible. So majority of load, since it is in MV, for this MV bus power factor, we need some control also. So this control is not available at present moment of time for us, and because of that, there will be huge distribution losses. Okay, So these are the challenges which is there with a complex power distribution. Our ILMS system, which is being conceptualized and designed in our Holtec, is a tool to address all these issues. Why? This ILMS or integrated load management system, what is this? This is a dedicated PLC based control system, and this is designed to achieve a high speed clearing of the grid fault or other critical faults, so that your system stability will be ensured. We can have priority based fast load shedding available. Less than 100 millisecond is also achieved with this system, so that the stability will also achieved, and we can give you the priority also, so that you can change the priorities of the load shedding breakers on real time. So that will give us a tool, so that we cannot have undue production losses. Okay, and this load shedding is being done based on the required amount of load which we have to shed. Say we need to shed say 5 megawatt load, then it can select 5 megawatt load and shed the load of 5 megawatt only, or maybe 7 megawatt, not unprioritized load, maybe 10 megawatt or 12 megawatt can be shut. Okay, so this in that way also we can prioritize and save production. Then we also provide backup df by dt and manual load shedding function, which is a backup to this fast high speed load shedding system. Then with that we can have balanced or unbalanced load sharing, balanced and unbalanced load sharing between generators. We can also control the power received from the grid. We can also control the power factor of the grid. We can also control the power export to the grid. So, and also we can manage active and reactive power on all sources and all buses, so that we can achieve the minimum losses in terms of distribution losses or losses in the sources, generators, and the losses in the motors, if we are managing the active and reactive power. Then the grid power factor, I have already told, power factor, grid power export, we can control. Then we can also have features like fast bus transfer. Fast bus transfer means we have multiple source. Now we have a situation where there is an overloading in one of the source, on which one of the bus is feeding, say power is feeding, a source is feeding power to bus number 1, and its load is increased to the capacity of the source. Then what will happen? Without having any interruption, this entire bus we can shift to another load where we have lesser loading, so that this bus with the load on those buses will not be affected. So this is called fast bus transfer scheme. So this is also possible through our integrated load management system, which we are actually designing in Holtec. This is a typical power distribution scheme. I am sorry, it is not very clear because of the size of the power distribution. Same thing, three transformers, 2 CPP and 2 WHR as a source, and multiple lines are there here. You see small dots here. In many places in power distribution network, you see very small dots. What is these small dots? These small dots are defined here. We define the area, the equipment or the tie breakers or the source system, where we can have either power monitoring, we can have either load shedding to initiate, we can identify the areas where we can have certain controls. Controls means controls basically on power factor, bus capacitors, controls on certain tie feeders to change the mode of operation if situation demands. So there can be a bus coupler, there can be a tie feeder which can be controlled uh, through this ILMS system. In addition to this, before we move further, let me tell you the load sharing system which we have defined, or grid power control system, or power control philosophy which we have discussed. How it is being achieved? Actually, what is happening? All our own source of generation, not all, critical loads, maybe critical, we can define the source which is the costliest one, and we can do the controls. Controls means their their mode of operation will be changed from fixed route to asynchronous mode. In that mode, the total control of this generator operation will come into the load setting controller. So based on the decision taken by the load shedding controller, the reactive and the active power delivered by this generator will be controlled. So in that way, if we take say grid power as a reference, with that reference we can do the variation in this generator power. So in that way, it is possible. It is possible in reverse. Normally, when we operate in parallel with grid, what is happening? Grid will be a fixed and all variation will be there in the grid, and generator will have fixed load. So if we take over on ILMS, then what is happening? The grid we can fix, and the variations we can take care with the various generators available in the system. So in that way also we can achieve. So the controls means generator controls, tie breaker and bus coupler controls, and bus capacitor controls. Then we have load shedding breakers, where we can which we can be operate based on the priority, and for taking any decision, we do the measurements on the various sources, various branches, various type feeders. We can do the power monitoring also, and the loads also, the power monitoring. This is the control architecture for our designed ILMS system. We have a controller, dedicated controller for this take. It is independent of all other activities. This is not your process controller, plant process controller. All informations which is required will be gathered by this controller through a distributed IO system, which is distributed at various locations in the plant, and will come to this controller. In addition to that, we have get the parameters from the generator, we have get the parameters from the various power monitors also. We get parameters from other relays also. Varieties of relays will be there that we have introduced, because of we need to operate the trippings also, fast trippings also. So all these informations will be there, and based on our logic which we develop in this controller, and with the use of SOE relays, which is very fast acting IOs, SOE IOs, sorry, SOE IOs, we can achieve the tripping of the load or tripping of the fault, clearing of the fault with less than 100 millisecond also. There are so many other parameters will depend, but we can achieve if if we do all required modification in the existing power distribution system. This is our various IOs which for a particular system we have designed. For all the areas we have gathered information. We have roughly more than 30 load shedding breakers here. So based on our requirement, we can prioritize all these 30 breakers on real time. Okay. This is the dashboard which shows the SLD in our ILMS system screen, where we can see the power pad, various parameters, status of the breakers, and the status of the other equipment and the tie breakers also. Okay. This is a screen for any ILMS system where you can have a priority table. So you can prioritize the load shedding loads based on your requirements on real time. You can change at any moment of time. And these are the predefined operating scenarios. So for any defined operating scenario, so suppose if we have priority number 3, but in any of the operating scenario, this is not activated. So our activated load shedding breakers in this scenario in all these scenarios are this only. So this is something which will be available for us. So we know what is going to happen in our system if any abnormality occurs in the system. Okay, and we can decide the priority which load we have to sacrifice. This is another way of representation, very informative for the people. What is the power which is from various sources we are getting, and what is the total plant load, what is the total source generation. Okay, in that way we can understand what is our auxiliary consumption also, that can also be identified. So all these screens are not fixed screens. These screens can be optimized based on the particular power distribution requirement. This is one of the example. Here the major emphasis is that the distance is not at all a problem for us. Even a 15-kilometer distance we can connect through the connectivity can be possible either through OFC, either any lease line link or wireless link. This is possible to get the information exchange and make the system entirely effective. You know, the power distribution system is unique for each plant, hence the problem and its remedial measure. What it means, you cannot make a prototype system, ILMS system. So when we design a ILMS system, it should be unique for every plant. We cannot copy paste one system which is running in one plant. We cannot copy paste to other system. Your one plant requirement is not same for other plant. So there is a uniqueness. So we have to have a specific design for your power distribution system, a complex power distribution system, ILMS system. Okay. with addition of multiple sources, if we are adding many sources, transient stability is strongly recommended for reliable operation, because we know the fault clearing time and we set our relays below that fault clearing time and ensure the transient stability. And if we have multiple sources or multiple lines, an effective ILMS need to be designed which shall be in line with our optimum operating requirement and operating power lines and power sources. So for multiple sources and multiple lines, we should design a ILMS system, okay, to handle this complex power distribution situation. Last, the effectiveness of any corrective measure, that means an ILMS system or a study which we do will be only effective when this has to be done by an agency which is not only having the proficiency of electrical power distribution, but it should also have an expertise in your plant system design and operation. So because the operation and electrical power distribution has to vary each other. So a agency which is not actually expertise in your is not having knowledge of your plant processes cannot give you proper design of the ILMS system. They cannot offer you the optimized way of this integrated load management system, and cannot analyze through ETAP studies the various aspect of the power distribution, like load flow, short circuit, relay coordination, and transient, etc., etc. Okay, so what we suggest you, we as Voltec would be glad to extend any help to study and give solutions for these kinds of problems.